So this very nice diagram, lots of lovely topics that are present in this person's head, and particularly focusing on the pre-geometry bit. So this is, of course, from Misner, Thorne, and Wheeler, and we know from the text what they had in mind. Here's the quotation. Bare bones quantum mechanics lends itself in a marvelously natural way to formulation in the language of the calculus of propositions, as witnessed not least the book of Jauch, that's Joseph Jauch's book, Foundations of Quantum Mechanics. I suppose that was a bit of a homage on Wheeler's part in particular to Jauch, but my talk is a homage to Howard. Okay, oh, I think you just missed that, the homage to Howard. Okay, so the structure of my talk, objects in general, I'll be brief on that. Objects in quantum mechanics, a conventional account, I'll spend rather more time on that. And then my real topic, I suppose, quantum monads, I'll come to that in the latter third or so of the talk. Okay, so in general, my standpoint is broadly Quinian. It's the view that we connect with ontology through speech, through sensation, through action in the physical world. If we're interested in regimentation and precision, we can go to something like predicate calculus, quantification theory, ergo Quine's slogan, to be the value of a bound variable. So we thereby engage in discourse about physical things. And my suggestion, and here I think I probably depart from Quine, is that in this form of discourse, it only goes down so far. We can't do better. There's a little, I'll qualify that statement in a minute, but broadly speaking, it's our only resource. The only way to connect objects in the micro world to everyday objects is through instrumentation, manipulation, control, observation, and insofar as we make reference to speech, quantification theory and speech. And the view that this is only going to go down so far is that, broadly speaking, all of this is parochial, that ordinary language, a kind of general purpose theory of the world, is parochial, and there's no reason to suppose it will be apt to regimes very remote from ours, very exotic, and so forth in scale and energy. Okay. Now, it's rather important in all of that that I'm distinguishing between physical and mathematical objects, a point I'll come back to in a moment. Up on the slide that you've got there, I've just got a general point about realism and quantum theory. Of the three main approaches, Pilot Wave and Everett, the micro-macro, meaning everything from ordinary objects down to large molecules, derive quasi-classical or phenomenological theories only by appeal to decoherence theory in terms of the unitary formalism. At the micro level, Pilot Wave theory, they have typically nowadays primitive ontology, where the field of particle configurations. In the Everettian case, it's open. What is the macroscopic ontology? How are we to talk about things? How are we to connect such talk about things to macroscopic structures? So that's very much my topic this afternoon. If we look at dynamical collapse theories, there just is no derivation of the micro-macro phenomenology. It's an article of faith that get the right fundamental equation for dynamical collapse people, that'll be something like GRWP, the non-relativistic realm where the theory only is defined there. But how do you go from that to all of the interesting, actually large variety of phenomenological equations? It's an article of faith. It's often been ignored by Pilot Wave people too, as far as those few that have considered it, and indeed the classical limit of Pilot Wave theory, they also end up appealing to decoherence theory. For some fairly detailed commentary along those lines, see Joshua Rosala's writings, my student, but not, may I add, an Everettian. He was not driven to such a point of view through lack of charity to Pilot Wave theory, on the contrary. Okay, and lastly, on dynamical collapse theory, what about the micro level? They're in the same situation as Everett, unless they adopt primitive ontology, something like the flash ontology or the matter wave ontology. I'll come back to those things in a moment. For now, I just want to make clear that the space that I'm interested in is what is this Everettian open or dynamical collapse open account of microscopic ontology? Okay. the first person, so far as I know, who really said something articulate, or at least along the lines that I think are important, about the distinction between mathematical and physical discourse about things was Gibbs. So this is in the last pages of his book. So it's very nearly his very last writings. So I'll read it out. If he's talking about the idea of an ensemble of gases, where each element of the ensemble represents a gas and a certain state of the gas, and he's considering those that differ only by permutations of particles. So he says, if the particles are regarded as indistinguishable, it seems in accordance with the spirit of the statistical method to regard the phases as identical. In fact, it might be urged that if the particles of one system are described as entirely similar to one another and to those of another system, nothing remains on which to base the identification of any particular particle of the first system with any particular particle of the second. And that would be true if the ensemble of systems had a simultaneous objective existence, but it hardly applies to the creations of the imagination. Okay, I think that's absolutely right. And to stick my neck out a bit, it seems to me that in mathematical thought is irredeemably indexical or hexaistic. To take plus I and minus I, can we make reference to the one rather than the other? It seems to me that mathematicians don't really know. I sometimes ask them this question, but typically yes, but goodness knows quite how that works. When it comes to physical objects, though, and I just focus on this point that Gibbs is making, if they're qualitatively exactly the same, then how do we base the identification of any particular particle with any other particular party? What he's asking for, it seems to me, is something like a Phrygian sense, but one which is physicalistically grounded. Okay. Let me go to the context very close to what Gibbs was considering. He was actually writing on the paradox that bears his name. But let me look to the quantum mechanical case, and taking my guideline from Wheeler et al., Jauch, and this parallel between the projection operators and propositions, it seems that in symmetrized, corresponding to a symmetrized quantum state of indistinguishable particles, we can speak of symmetrized quantum one-particle properties, symmetrized projections, so here R and Q. The exercise I'm interested in is how do we mimic this kind of structure in the predicate calculus. And a fairly obvious line of thought is we should look at symmetrized one-place predicates. That's on the syntactical side. And on the semantic side, we have a set theoretic model. Okay, so we can think of R is round, Q is cubic. So we've got a disjunction of A is round and B is cubic, or is it the other way around? Fine. Now, the issue arises, and this has been pushed recently by people like Das Gupta and Ted Sider, many other people, what grounds this equivalence? What grounds the disjunct? And at first sight, it seems there's a problem insofar as the set theoretic model will make true one or other sides of the disjunct. It won't make them both true. Let me put pressure on that. So in the quantum mechanical case, indeed, we can look at the unsymmetrized quantum state. Now, that will make true in the sense of eigenvalue 1, the symmetrized projection, and it will do so by virtue of being an eigenstate of one or other of the disjuncts. So looking at that, really a choice we have on the quantum mechanical side, on the semantic side, looking at the state, what corresponds to the symmetrized quantum state? The set theoretic model is giving us the unsymmetrized state. What corresponds to the symmetrized quantum state? Okay. Now, I don't think there is no answer to this. Well, hold on, actually, I didn't mean to put that up just then. Typically, it seems to me, if we're talking about the world, we need to get the syntax right. We need to get the sentences right. What we're talking about, after all, is reality. The set theoretic model is a creation of the imagination. So in a sense, I'm not too bothered if imagination, maybe we're going to have to do something fancy at the set theoretic level, for the model, but this is a creation of the imagination. But what does matter is discourse about things, reality. And at that level, I have it in red. What about the quantified sentence? Or we could go to something more like a property bundle view, the R, the Q. And note that the existentially quantified sentence, from it we can deduce the disjunct. If we have names in the language, we can deduce the disjunct. We can't deduce either term in the disjunct. Okay, let me add more support to that. If we look at the symmetrized state, a special type of symmetrized state, indicated top right, from that we can go to one particle states. So rather than understand the quantum state to be this entanglement, we can just say it's a pair of one particle states. And that seems to line up quite well with what's happening in the predicative case. Okay. And the implication, or the suggestion I want to make, is that proper names are just like positions in tensor products. They have that role, they play that role. And what's going on with symmetrization, of course, is one's obliterating the significance of position in the tensor product. One retains the tensor product structure, but obliterates the distinctions thereby created because it's a sequence. One can speak of place in tensor product. And that lines up, as I say, with proper names. Fine. The same thing should apply, if anything, if this is right at all, to positions in Cartesian products. So that's what I want to explore. Let's look at how that works. So in the quantum mechanical case, we go from the unsymmetrized Hilbert space and vectors in that, and we look at their superposition, the entanglement. In the classical case, we go from phase space, where we've got sequences, and the analog from going from the unsymmetrized Hilbert space to the symmetrized Hilbert space is going from a phase space description where we have 2 points related by permutations, they're distinct points, but we go to the reduced phase space, we just end up with the pair of particles, an unordered pair. And going back to whether we've got property bundles or existential quantification, it seems to me this is exactly the sort of example where the lineup, the match between predicate calculus and the apparatus that we use in physics, the state space apparatus in particular, isn't quite clean. Perhaps we have to make arbitrary choices. Perhaps we have to put up with a less than transparent correspondence. But I don't think it's bad. Let's just see how this works in well-known cases. So I assume that everybody is pretty familiar with this stuff. So here's the unreduced classical phase space. I'm working at the level of quasi-classical methods, really, to capture quantum characteristics. So at the level of the unreduced classical phase space, I've got a coarse graining on that space. Well, we imagine it as being a pair of coins, heads and tails, and I've got a finer graining. So whether it's heads or whether it's tails, there's a finer graining possible, perhaps the color of the coin or something like that. Okay, so now observe that the cells along the diagonals have no partners, unlike those off the diagonals. Correspondingly, if we look at a volume measure, and we use that to define probabilities, the probabilities of having the two coins with identical properties is only half that of having them with non-identical properties. Okay, and that's totally familiar. The probability of two heads is a quarter, probability of a head or a tail is a half. Fine. Go to quantum mechanics. Oh, sorry, go to the reduced state space. Now we give up the use of proper names to distinguish the particles. We no longer have that apparatus for describing the particles in these two diverse ways, when they're interchanged and when they are not. We just have, if you like, the unordered pair. Still, it's the case that the probability measure, the volume measure, assigns half the volume to those on the diagonals to those off the diagonals. Okay, in other words, going to the reduced state space in classical physics makes no difference, right? Quantum mechanics makes all the difference. Now, why? Instead of a phase space with a smooth volume measure, we have a vector space structure. The measure becomes the dimensionality of subspaces. The measure that is used assigns equal dimensionality to all of the subspaces of the same dimension. So I'm looking now, corresponding to not the coarse graining in terms of heads and tails, but the finer graining. Suppose that fine graining are one-dimensional subspaces. We have 10 in all, and they're equally probable. So now we see a departure from classical statistics. Now the states along the diagonal are assigned comparatively higher weight with regard to those off than in the classical case. Okay. And it's clear why it's rather important that the coarse graining, or rather the fine graining that I'm talking about, is a subspace of low dimensionality, where at high dimensionality, so such as I'm indicating now, suppose that there are many more subspaces in comparison to the fine graining that I had before. The number of states in which of all of equal weight, well, almost all of the available states have equal weight, equal to, that is, the classical assignment. The ones along the diagonal become less and less significant. They contribute less and less. We approach classical statistics. Okay, fine. Now, if any of this actually is related to anti-hexaetism, if abjuring the use of proper names amounts to anti-hexaetism, and that amounts to using the reduced phase space, then it seems clear to me, I put it to you, that anti-hexaetism combined with other principles can be physically significant. And I like to think of this as a little bit like how many definitions do you have to put together before you have something which is factual? The question isn't really that interesting, but certainly that they acquire critical mass, you have an empirical import. That seems clear in this case. All right, so let's go now to the issue of how do we treat names? How do we recover names? So if our state space structure is one in which, if the dynamics is such that certain regions of the state space are inaccessible, specifically those in which the two bodies in this case have the R and G properties, red and green, then the available state space is as shown in white, and the structure of that available state space is just the unreduced state space for two things, one R, one G. So this dynamical property of being red, being green, that was going to be stable through the dynamics, leading to these inaccessible regions of the phase space, are functioning just in this simple case of two particles as proper names. More generally, how do these stable dynamical properties come about? We need quantum mechanics for that. How do we go from a collection of protons, electrons, and neutrons to a very large variation of things, natural kinds, exactly through these stable dynamical properties, being a bound state yielding oxygen, being a bound state yielding hydrogen, and so forth. And if we can go to small numbers, then these natural kind terms can really function like Russellian definite descriptions. Okay. Well, I take all of this to be a success story. But what of genuine non-trivial entanglements? So what I have on the right-hand side here are symmetrized states that arise by taking a collection of one-particle states. This is cleaner when they're orthogonal, and symmetrizing them. So you can go back and forth between the symmetrized state and the collection of n one-particle states. But what happens when you've got superpositions of such symmetrized states? And now it seems there's a problem. One thing you might try to do is go to the four, just take the example that I've given on the top left, go to the four one-particle states involved, but it's pretty clear that this is a hopeless approach. As you get more and more complex superpositions, the numbers of one-particle states goes up without bound, supposedly they're just two particles. And anyway, this doesn't characterize the phase relationships among the various states entering into the superposition. So non-trivial entanglements poses a further challenge to objectival talk about quantum mechanics. It's supposed to be somehow capturing what is quantum mechanics, what is distinctively quantum mechanical at the level of ontology. It seems that we can still talk about things, we can still have existentially quantified descriptions, but the predicates involved are going to be somehow unanalyzable. They're just going to correspond to being in a certain entanglement. So that seems perhaps not a defeat, but a disappointment. One would like to do better. Let's look again at these various approaches, but now not so much with an eye to the particles, but with an eye to the quantum state itself. It's in this terms that this genuine entanglements are usually addressed, trying to get some metaphysical picture of what the quantum state is in the case of genuine entanglements. And now it seems pilot wave theory, everett, and dynamical collapse are all in roughly the same situation. Why? Because they, all of them, have the quantum state as part of their ontology. Well, I say that. Of course, there's a whole direction in pilot wave terms towards regarding the quantum state as something more like a gnomic thing, a dynamical law, not a part of the reality. The reality is just the Bohmian particle. So there's that sort of a move. But those who resist that move and wish to account for the quantum state as being somehow part of the physical world, what is there to say about that? So there's wave function realism, complex field on a 3n-dimensional space. Various people who have proposed that. Suffers from the problem of what about change in particle number, quite apart from the business of understanding how to recover from a complex field on a 3n-dimensional space, anything like the conception of the world that we have. Space-time state realism, a density matrix valued field on 3-dimensional space from Wallace and Timpson. Matter density realism. Now there's supposed to be something over and above the quantum state, or at least in primitive ontology ways of thinking about dynamical collapse theory. Certainly Garadi has embraced, I'm not sure about the primitive ontology, but the matter density realism. And now the position that I'm trying to defend, quantum state structuralism, or structuralist understanding of the state, indeed as a superposition of decoherent histories. And that perhaps works only for Everettians. I'm not sure whether that's available to anybody else. Okay, now the worry is that what I'm left with, I can perhaps account for the quantum state at the macroscopic level. I can account for the quantum state as the universal state, shocking perhaps as the ontological implications are, as a superposition of decoherent histories, but that all that the Everettian has to say at the level of the microscopic, well, there's the density matrix approach, but otherwise is a very thin notion of object using these unanalyzable predicates. So it's with that in mind that I really come to the third part of the talk, quantum monads. Is there something better than this rather informative predication about objects at the properly quantum mechanical level of genuine entanglement? Is there something more that one can say? All right, so for this part of my talk, I need the quantum histories formalism, and my apologies if that's foreign to anybody. If you don't know anything about it at all, this will perhaps be a bit difficult to follow, but I'll try to make it as intuitive and simple as possible. So start off with the idea of, indeed, go back to one-particle states, which are well localized in position and momentum. We can have a bit more degeneracy than that. These one-particle states need not be one-dimensional. Consider projections onto small regions of phase space. It's sometimes said you can't have such projections. Von Neumann actually showed us a way to define projections that are more or less do this function, projecting onto regions of phase space. Everett, interestingly, made reference to this, building blocks of reality. So consider associated projections and assume that they are decomposition of the identity, so they sum to one. So the crucial move to go to quantum histories is to index to times. so Heisenberg picture analogs, as indicated. And now what I'm doing here is I'm going to drop the explicit TK time dependence and indicate the time dependence in the subscript to the alphas. So alpha K is indicating that we're looking at the time TK projection operator, but that corresponds to a particular region of phase space. Right. So, okay, so given a sequence, define histories as the product of these Heisenberg picture projections. The quantity on the left, the C subscript alpha with a little line underneath it, that's just indicating that alpha is a sequence, usually called class operators or sometimes chain operators. We can coarse grain the projectors in the standard way, just summing over them. Rather elegantly, that induces, well, doesn't induce, we can just equally just sum over quantum histories, these chain operators, and coarse grain them as well. Okay, so this sort of coarse graining is pretty fundamental to decoherence theory in general. I would say more broadly than that, it's pretty fundamental to most ways where we go from a fundamental theory to a approximate phenomenological theory. And can I add that the histories involved, certainly when they're decoherent histories, are usually defined not as I've just set it up, but in terms of equations arrived at through integrating out degrees of freedom. So those equations we can, as it were, structurally represent what the quantum histories are in this way, but this is, in a way, a sort of a schematization of what's going on. The equations really come first. Okay. The move that I want to make now that isn't, I think, very familiar in the literature is to define compositions of configurations. So I'm doing that just by taking the product of the associated projectors. I'm assuming commuting. That's not a significant constraint, I think, insofar as I ask you to temporarily at least think of them in terms of tensor product structures, where, and we're not dealing with indistinguishability here, where the place in the tensor product is indicating a distinct system. So we may have a large collection of systems, and we have correspondingly a large tensor product structure. And if we consider projection operators which are identities in all of the tensor products except for one, it's clear how through taking these products, really composing these degenerate histories, we arrive at a less degenerate history. So that's the name of the game. So this extends to histories in the obvious way. I've got a sort of diagram. I don't know if that makes it more intuitive, but one's really interleaving these, each segment of each history through the composition operation as I've just defined it. Now, call history alpha possible in state psi if top right condition is satisfied. So this is the chain operator is not a self-projection operator. It's a POV. It's not a projection operator. So, but anyway, this is just the squared norm of the state C alpha acting on psi. And call histories alpha and B compossible if each of them is possible, and again if the same condition applies to their composition. Okay, now let me talk about decoherence. If we do have decoherence, we can define the probability of histories relative to one another. So, well, in my own work, I've often done this in terms of segments of histories entirely preceding one another or following one another. This is histories that interleave with one another, so something more general still. Very simple how to do this, to look at the probability of an event relative to a history. Just embed that event in a trivial history where prior to time tk, one has nothing but identity operators, and post tk, nothing but identity operators, and then apply the formulas I've just given. So this is a generalization of the two-vector formalism of Aharonov et al. To essentially arbitrary n-vector formalism, if you like. When I say it's a generalization, if it's restricted to decoherent histories, then that's going to be a restriction that Aharonov and his co-workers ignored. Indeed, the interest of their approach for many was precisely that you were led to some pretty extraordinary claims about these events singled out by the two vectors. What's going on with that is they're not using decoherent histories. Now that also, of course, signals a possible way of generalizing what I'm doing to cope with non-decoherent histories. Right, I'll come back to that point in a minute. Okay, something else. If the histories have branching structure, then there is a unique history, alpha, terminating in alpha at time tn. Alpha, the second occurrence is just a single element. The first occurrence, alpha, with a line underneath it, is the history terminating in alpha. So if branching structure, then the probability, so this is like a retrospective probability of beta conditionalizing on alpha n, is 0 unless beta equals that unique history alpha bar. And typically, if we're looking at coarse grainings of phase space, histories do have branching structure. And this is what gives rise to the familiar Everettian picture of a branching tree where the trunk is thicker, on each divide, things get thinner and thinner and so forth. There's a unique way to trace back from the tip of a branch all the way down back down to the trunk. That's branching structure. Okay, let's see. And I just want to emphasize, this is the only slide which mentions probability or assumes decoherence. Everything I've said, apart from what's on this slide, applies equally to the ultramicroscopic level, where we don't have decoherence. The definitions of possibility and compossibility do not require decoherence. Okay. Final point. So, what if we give up the tensor product structure? Remember, I was equating the tensor placement and tensor product with proper names. If we give up the tensor product structure altogether, then no two histories can be exactly the same in the following sense. The compossibility, the composition of one history with one identical to it just yields the original, and that by idempotence. So I've given you the proof. Under what circumstances would we give up the tensor product structure? Well, in a certain sense, we can retain it, and my point just made applies. And those are the circumstances where the tensor product structure is really being used to distinguish different degrees of freedom, which is very often how it is used. So with that use of the tensor product structure, of course, it's never the case that a configuration in one place in the tensor product with respect to certain degrees of freedom can be the same as a configuration of other degrees of freedom. Okay, so you only get the notion really of identical histories insofar as the place in the tensor product structure is being used to distinguish, as it were, entire systems one from another, rather than breaking down a system with respect to different degrees of freedom. All right, so let's just sort of review what I've done, where this is all coming from. In a certain sense, my claim is that everything that I've said is completely uncontroversial. There's no speculation involved at all. Now, that's the case. If we start from a history space, and especially if it's a decoherent history space, then the comments I made about correlational structures and so forth kick in a well-controlled way. So if we start from a decoherent history space, we start from a single history belonging to that decoherent history space. And we, through coarse graining, break it down into multiple more degenerate histories. Well, we know that they're compossible. We arrived at them starting off with, as it were, the full history. Now, if you take quantum mechanics seriously as a fundamental theory that governs all of reality, okay, we've got gravity, but you take my point, then at some level, the reality that we're presented with, what we're doing in the special science is reverse engineering it to work out what local histories it is composed of, what quasi-local dynamics. Remember, these histories really correspond to equations, dynamical equations. What quasi-local dynamics, each with its own decoherent history space. So that's the project that anybody who is serious about using quantum mechanics in the special sciences is doing anyway. Whether they may not use the decoherent history formalism, of course, but they will be using decoherence theory at some level. And insofar as they don't know what it is that they're doing exactly, but they're using effective equations that are well known to be useful, someone with a better ear for quantum foundations can come along and fit that into this context. So, slightly chauvinistic, but the claim is this is just doing the special sciences, but it's doing it in a distinctive way. It's another matter to actually try to set out a framework where there's a global decoherent history space where each history has this hugely complex and rich structure that we see in the actual world, taking the actual world to be one member of that decoherent history space. So whether anything like that could ever be arrived at is speculation. But I think it's the same sort of speculation that goes into those who resist the Cartwrightian picture of local patchwork, patchwork of laws without any overarching unification. Anyone who's interested in unified science, I think, is part and parcel of this project to try to understand the world in all its complexity as governed by fundamental physical laws. And now the question is how far can we go in defining a decoherent history space adequate to the full complexity that we actually see. Okay, so I want to go now look at it, doing it the other way, not as it were, well, actually, I want to realistically speculate on how we might arrive at that. How can we arrive at that decoherent history space such that the histories involve the full complexity and variety of the world that we see? And the one way to do it, can we work out a way of building up from histories, taking from diverse decoherent history spaces, each with its own equation? Okay, so now, is that something that can be done? Well, there are certainly people who work on this sort of project. Jonathan Hallowell is an example. It's a way forward. Another way forward, of course, is really not taking the history space perspective seriously, but looking at more things like environmentally induced decoherence, although that's just a particular kind of decoherent history space. One can imagine doing phenomenological building up to interesting systems, working with things like Gaussian states and so forth in a more incoherent way. I'm talking about this is a systematic approach. Anyway, so this is one question. Another question is this: can we work out a way of defining correlations between histories that are not decoherent? And this second question seems to me a very different question, in some ways a more speculative question. It's not clear that anything like this can be done. But I come back to Aharonov. It seems to me that there has been some progress of this kind. People like Chris Isham, for example, have long championed the use of, he talked of not consistent histories. It's a bit of a shame to call them inconsistent histories. It suggests you've got a special problem there. But anyway, so there are people in the quantum gravity community who have championed non-decoherent history methods. Okay. I mean, with an eye to my skepticism that talk of objects, physical objects, that connects with talk of ordinary things, my skepticism that this really does go all the way down is actually inclines me to skepticism about this second question. But I'd be delighted if it worked out. It's not that I have a gripe with it or something like that. No, I mean, wonderful if it could work. I don't know whether we can hope for as much as that. But on question one, it seems to me that absolutely this is what many people, indeed in some ways, the major part of physical science is all about when you're looking at material science, kinetic matter. Okay. All right, so monads. I hope that I've carried my audience enough to see the obvious parallels, but for those for whom it isn't at all obvious, let me say a few words. So to start off, and may I just say just change of terminology, go from histories to substances. substances to monads. I think there are questions about that. History is clearly a four-dimensional thing. The substance less so. History may correspond to a process. That seems to be a temporally extended thing. What did Leibniz mean by monads? What did he mean by a substance? But my talk isn't really, I'm not very preoccupied with whether it's an exact match with Leibniz, and of course it isn't an exact match. How good is the match? I don't know. But in certain respects, it seems to me they're very sharp, striking parallels. So substances are windowless. That these substances, they don't interact one another, according to Leibniz. And of course, quantum histories of the kind that I've been considering, they don't interact with one another either. They are correlated with one another or not correlated with one another, and that is all that one can say. The passing state, which involves and represents that within the unity or simple substance, is nothing but I've got windows up on my screen. I can't entirely read everything that that you can read. So there's nothing other, I think, than what is called perception. Well, I'm talking about sequences of projection operators, where the projection operator, in a sense, is, I can't think of anything better fitted to be called a mirror or a perception of the whole universe. But I'm not going to defend that. It either works for you or it doesn't. For each substance, there is a complete concept from which every true predication of it follows. But that goes without being clear. I'm talking about, for me, a substance. It is one of these decoherent histories. It's the entire. Every predication of it follows, of course. The passing state of a substance involves all that has ever happened to it. If you've got branching structure, that's true. But to have branching structure, notice you need a pretty fine-grained level of description. You coarse grain, you lose the branching structure. And that seems to accord with a lot of things that Leibniz said about monads as being more or less precisely representing the universe of which they're a part. He spoke of confused perceptions and things like that. And he also spoke of dominant monads as opposed to subjugate monads, in terms of which determines more of the other. Precisely some of these statements could be made of decoherent histories. There is no relation between two substances that is not determined by their intrinsic denominations. Indeed not. I spoke of the quantum state. From the Everettian point of view, you might as well take it as the vacuum. So in the vacuum state, all of these decoherent histories have various correlations with it that we understand from the models that we so have developed. So all of the structure, in a sense, is in the histories. And of course, those histories involve the dynamics. These are Heisenberg picture structures. The Hamiltonian is involved at each stage in the description of the history, the substance. A possible world is an aggregate of compossible substances. Well, that goes without saying. For each substance, there is a law. For each aggregate of compossibles, a law of the aggregate. I spoke of equations. The time series of a substance cannot begin or end other than by creation or annihilation. Well, these histories, there's no way to just cut them off, if you like. All you can do is add identity operators at either end. They can only end in, well, what also Leibniz also spoke about, a sort of state of dormancy, where there's no representing going on anymore. That seems precisely the situation with these decoherent histories. There may be a way of making sense of creation or annihilation in quantum field theory. So there's parallels there. I'm not discussing that. And finally, no two substances differ in number alone. We've discussed that already. Okay, so thank you very much. I return to my image that I started with. Perhaps you'd like to read what was written above it. And as imagination botters forth the form of things unknown, the poet's pen turns them to shapes and gives to airy nothing a local habitation and a name. William Shakespeare. I call it a homage to Howard. Howard asked a question a number of years ago that I found, and that many others found, enormously provocative. Why is a thought so long and thin? I haven't spoken about other aspects of Leibniz's philosophy bound up with mind-body relationship. He thought the monadology dealt with the mind-body problem in a wholly satisfactory way. Whether a neurophysiological process can be understood as anything like a decohering history in representation relations with other forms of matter, I don't know. But thank you, Howard. You've been an inspiration to us all. And thank you all.
Can you hear me? No. No. All right, bye. So, I'll grab that recording.